Yeah, hello guys. So welcome back to the session. Sorry for the delay. There was a small technical issue actually from the camera side, but I hope things are fine. Okay. Now I hope I'm audible and the video is clear. Guys, please confirm the audio and video once. Is everything fine? Fine, right? Yeah, no issue, correct? Okay. Good evening, guys. Just please confirm because I think there was still the issue, but I hope it's fine, right? Yeah, it's good then. Thank God. Fine then. Okay. So welcome back with certain uncertainty again in the beginning. So no issue, right? Yeah, good. So we'll continue this series, and today is going to be the last lecture of this linear algebra. Okay. So in tomorrow's class, we are going to start single variable calculus again. But in today's class, basically we have a lot of nice things to learn. See, basically till now I did not teach you the techniques of solving the linear systems. Okay. So we will see the techniques for solving linear systems like the Gauss elimination. Okay. And then after, basically I'll teach you LU decompositions. Okay. And we'll see SVD also, singular value decomposition today. And we'll talk a bit of partition matrices, and prior to all these things we'll also talk about vector spaces. Okay, so in today's lecture today is lecture number 8 basically of linear algebra. And basically in this today we also have one thing. Basically in this channel, when I say PW, we are going to take Telegram live after the class. Okay, so Telegram live is what we have, where you can just interact with me. Okay, so if you have any doubts or anything, you have any concerns about anything, you can join this chat and we can have a nice discussion about this of course not only this mathematics, but of course in regarding any general queries like GATE examination or any PSUs or anything. I'm going to start a live at around 9:05 or 9:10 today after the class immediately. So we will actually start the live session. Okay, and also for any update on this channel, like for example from tomorrow we are going to start single variable calculus. So all these updates will be rolling up on this YouTube channel, Wallah English, and for that we have a Telegram channel with Wallah English Telegram channel, and this is the code which guides you directly to that channel clearly. Okay, so we recommend you to suggest to basically scan this and join the group so that you don't miss anything. You'll have regular updates on the things. Okay, and of course I'll always talk about this U Infinity, which is a very powerful platform. Again, it can have a record of all your queries at one particular location. Okay, and all your notes at one particular slot actually. Clear? So that's what we have. And of course in this Unity we can have the lot of features like basically the video call or basically polls connecting and all, and it keeps a track record of all your data at one point. The only thing you have to do is whenever you're typing comments in the YouTube, if you have a doubt, then just before the doubt you can just type this exclamation doubt and then you start typing your doubt. Okay, similarly if you want to add a note point, then click as this exclamation note and then type your point. So all this will get stored in your Unity platform, which I have shown of course. Okay, so coming forward to today's class, so in the last lecture our main prime focus was on diagonalization, eigenvectors of course. So we initially talked about eigenvectors and we have also talked about diagonalization concepts. Okay, so diagonalization is one crucial thing which we have talked about. Like if you take a matrix A, then as long as it has linearly independent eigenvectors, so if you have this linearly independent eigenvectors, we can frame this matrix A is equal to P D P inverse. So a few people they are habituated to write this as D equal to P inverse AP. Of course both are same. If you keep multiplying with P inverse, then P with P and post multiplications, you'll get D is equal to P inverse AP, which is that. Okay, so you'll generally see all these things. Clear? Okay, so at 8 PM today all GATE faculty connect via Zoom calls. It's okay, fine, no issues. Okay, so let's see. This diagonalization is one thing which we have seen. So this diagonalization is basically for calculating higher powers or for solving systems. Solving systems is what we have seen of course. Okay, and I have also given you some ideas about diagonalization. Whenever the matrix is diagonalizable, then ultimately we get sum of geometric multiplicities, sum of geometric multiplicities is equal to n of course. Okay, so we have seen sum of arithmetic multiplicities is obviously equal to the size of the matrix, and that is equal to sum of geometric multiplicities as well. Okay, and I have also given you one important point. Rank of any matrix A is equal to this n minus sum of course square matrix. We are talking about square matrices, sum of basically n minus algebraic multiplicity of of 0 as an eigen value, of course. Okay, so 0 as an eigen value. This is what we have seen, and we have generated this. Basically, we have checked this with 1 or 2 questions, like 4 to 2 to 4 to 2 to 4 system. Then for that matrix, we have seen rank is 3 because that matrix don't have any 0 as eigen value, of course. Okay. See, if you have doubt, yeah, please type. It's fine. Okay. So exclamation doubt, and then you keep typing. No issues. Now, I have given you one homework question actually. So this is the homework question what I have given you. Let I denote the identity matrix of order 7 and A be a 7 by 7 real matrix having characteristic polynomial CA of lambda is equal to this. Okay, so this is the characteristic polynomial. Of course, lambda minus 1 whole power alpha is only once. Okay, sorry, it got typed twice, I guess. So lambda minus 1 whole power alpha, lambda plus 2y power lambda plus 2 whole power beta. This is what you get, where alpha and beta are positive integers. If A is diagonalizable and rank of A is equal to rank of A plus 2y, then rank of A minus I is dash. Okay, so rank of A minus I is dash in integer. So let's see. So will ICRB come this year? Yeah, generally it's expected to come because, but of course may not be this year, but in the upcoming year 2025 it can come. Okay, the reason is whatever the equipment they have posted in 2023, that exam got happened in January 2024 this year, and the shortlist for the interview has not come up yet. Okay, it's been almost some 4 months, but it's awaited still. So I think that same list will continue. Okay, so how to think about such problem? Which problem? I think your comment was deleted, but please retype it. Okay, so now let's see. In this case, I have given you a hint in last class. So if you have any polynomial equation or any equation in general, x square minus 2x plus 1 is equal to 0, for example, let's say this equation has got roots alpha comma beta, or if you have f of x is equal to 0 in general, which has roots alpha comma beta. Now if you want to have an equation with alpha plus k comma beta plus k as roots, then this is f of x minus k is equal to 0. This is what we have seen yesterday. Okay, so if you want to have a roots which are alpha plus k and beta plus k, then f of x minus k is equal to 0 is the equation which has this corresponding roots. This is the hint I have given you. Okay, now using this particular hint, we can easily solve this question. Let's see how we can solve this question. Now see here, there is a matrix A of size 7 by 7. Okay, so this is of size 7 by 7. So clearly the characteristic polynomial of this matrix would be of 7th order. Correct? So if this is a matrix of order 7 by 7, ultimately this characteristic polynomial, if you take, this is of order 7 or degree 7, of degree 7, of degree 7 ultimately. You know this. Okay, this is actually one of the toughest questions which I wanted to solve because I'm solving only easy to moderate. So I thought of solving one nice question. This question came in XE, where maths is generally a bit higher level. So this question is from XE, previous year question, of course. Now let's see, this is a 7 by 7 matrix, and characteristic polynomial CA of lambda is equal to lambda square into lambda minus 1 power alpha, lambda plus 2 power beta. This is what you have. Okay, this is the characteristic polynomial. Now if this is characteristic polynomial, then let's see, if this is your characteristic polynomial, definitely this characteristic polynomial should be of degree 7. Okay, because the matrix itself is a 7 by 7 matrix. So that means this is power 2, this is power alpha, and this is power beta. So 2 plus alpha plus beta should be equal to 7, or in other words, you can say alpha plus beta is going to be 5, of course. Correct? Yes or no? Are you all clear with this part? Please type in the chat box. There will be many equations with roots alpha plus k and beta plus k. No, if you fix alpha k beta, then there is only one quadratic equation which has the roots. No two quadratic equations will have same roots, obviously. Okay, clear? So no two quadratic equations will have the same roots. Yes. So ultimately, it's, if you have a particular roots, then you have a particular equation ultimately. That's what, right? Otherwise, whatever the equation they ask us to solve, we can, you know, you can solve any equation and tell that these are the roots of any other equation. Okay. Now let's see. And what for this noise? Didn't get you. Look, basically what we were talking is, we have seen how to calculate the characteristic polynomial. Okay, and if you have the characteristic polynomial, then this characteristic polynomial is obtained by that of a minus lambda I is equal to 0. Correct? Now if the matrix is of size 3 by 3, ultimately a characteristic polynomial is also of third degree equation, a third degree polynomial equation. Now since here it is a 7 by 7 matrix, so ultimately the characteristic polynomial, if you calculate that of a minus lambda I, you will have a polynomial which is of degree 7 clearly. Okay, so that tells you this, if you add up the powers, this is square, this is alpha and this is beta. So if you add up these powers, it total will sum up to 7 because this is a 7 by 7 matrix. So that means alpha plus beta is equal to 5. Yes, is it clear to all of you till this point? Yes or no? It's a nice question which involves a bit of concepts, so I have put it here. So alpha plus beta is equal to 5, correct? Yes, but adding powers, how 7 comes here? Because the total power has to be 7, correct? That's what. Now let's see one more thing. You can understand one point. If you equate this to 0, for example, if you equate this to 0, ultimately you will get 7 roots. Can you tell me, since there is lambda square here, how many times you'll get 0 as eigenvalue? Can anyone tell this? This is total of degree 7, but it has got lambda square. So if I equate the CA of lambda equal to 0, then how many times I'm going to get 0 as a root of that equation? Twice, correct? So that means you can see for CA of lambda is equal to 0, we get algebraic multiplicity of lambda is equal to 0 as 2 clearly, correct? Means 0 comes twice if you equate this equation to 0, correct? Now this implies rank of A is equal to, it's a 7 by 7, so 7 minus algebraic multiplicity of 0 as eigenvalue is 2, so rank of A is actually 5 here, correct? So this rank of A is equal to 5. Now let's see what else they have given. Alpha and beta are positive integers, of course. A is diagonalizable and rank of A is also equal to rank of A plus 2i. Okay, so this is the main important thing. Rank of A plus 2i. Try to understand. Rank of A is equal to rank of A plus 2i. Okay, now you know one thing. This is 5, of course. This term is 5. Okay, now what is rank of A plus 2i? Rank of A plus 2i is nothing but 7 minus algebraic multiplicity of 0, algebraic multiplicity of 0 as eigenvalue for A plus 2i. Yes or no? Correct? Will you all agree? Yes or no? Anyone? So please type in the chat box. Will you all agree with this statement? If I talk about rank of A plus 2i, this is nothing but that if A is of size 7 by 7, A plus 2i is also of size 7 by 7 ultimately. Okay, so rank of this matrix is nothing but 7 minus algebraic multiplicity of 0 as eigenvalue for this matrix. Correct? Yes or no? Please type in the chat box. 2. Now let's see. If you want to know what is the algebraic multiplicity of 0 as eigenvalue to this matrix, you should know characteristic polynomial of A plus 2i. So considering characteristic polynomial of A plus 2i actually. Okay, so what is this characteristic polynomial? Now tell me one thing. If A has eigenvalues lambda, then A plus 2i has eigenvalue lambda plus 2, correct? Yes or no? I have told you this point. During properties of eigenvalues, I have told that if A has eigenvalue lambda, then ultimately A plus 2i will have an eigenvalue A plus 2. We have shown this in fact. Okay. Now let's see. For getting root as lambda, you have the equation as CA of lambda, of course. Okay. If you solve this, equate it to 0, then you will get lambda as one of the eigenvalue. Now try to understand one thing. If you want to have an equation which has a root lambda plus 2, okay, if you want to have an equation which has a root lambda plus 2, the equation which has the root lambda plus 2 is nothing but CA of lambda minus 2 is equal to 0. Yes or no? Correct? CA is the polynomial. So if the roots has to be 2 more than lambda, then ultimately CA of lambda minus 2 is equal to 0 is the characteristic polynomial. Correct? Yes or no? Please type in the chat box. Is this clear to all of you? Correct? See, what I am telling is, if you want to know a polynomial whose roots are lambda plus 2, then ultimately this is CA of lambda minus 2 equal to 0, because when you solved CA of lambda equal to 0, you are getting lambda values. Okay, so if you want to form an equation which is lambda plus 2, then ultimately this is what you will get. Correct? See, basically if you want, just a minute, okay, fine. So see here, if you have an equation f of x is equal to 0, you got the value of root as x. Now if you want an equation whose root is x plus k, you have to solve this equation f of x minus k is equal to 0. Correct? So same thing. Okay, the eigenvalues got increased by 2, so ultimately the corresponding characteristic polynomial would be CA of lambda minus 2 equal to 0. Is this clear to all of you? Is this clear to each and every one of you? Please type in the chat box. If there is any ambiguity, please let me know. What I am telling you is, if you solve this equation CA of lambda equal to 0, the solutions are lambda. Now if you want to form an equation whose roots are lambda plus 2, this is what the equation is. Correct? Yeah. Now therefore this equation is nothing but, therefore CA plus 2y of lambda will be equal to, wherever there is lambda, you have to replace lambda minus 2. Correct? So this becomes lambda minus 2 whole square, because here it is lambda, so I am replacing lambda minus 2, lambda minus 1, so lambda minus 2 minus 1. Okay, because instead of lambda I should put lambda minus 2 now. So this power alpha. Now again, lambda plus 2 whole power beta is what you have, lambda plus 2 whole power beta is what you have. So instead of lambda you are putting lambda minus 2 plus 2 whole power beta. This is going to be the characteristic polynomial of this matrix A plus 2y actually. Okay, now if you simplify this, lambda minus 2 whole square, lambda minus 3 whole power alpha, minus 2 plus 2 cancels, lambda power beta actually. Okay, which means if you calculate the eigenvalues of A plus 2y, you will get beta times zeros. Okay, means basically algebraic multiplicity of 0 as eigenvalue is going to be beta actually. Okay, so therefore rank of A plus 2y is equal to 7 minus beta, because beta is going to be the algebraic multiplicity of 0 as eigenvalue. 2. Yes, is this clear to all of you? Is it clear again till this point? Rank of A plus 2y is going to be 7 minus algebraic multiplicity of 0 as eigenvalue to this. So therefore this, because obviously if you equate this to 0, you will get beta times zeros as solutions of this equation. Correct? Let's say for example if you equate x cube equal to 0, then you have 3 zeros, right? Of course in the real calculus, we are dealing in a real calculus. Okay, now therefore, but you have one point, they have clearly given rank of A is equal to rank of A plus 2y, that's given in the question. Rank of A is equal to rank of A plus 2y, that means this left hand side is 5. 5 equal to 7 minus beta, so this implies beta is equal to 2, of course. Okay, so beta is equal to 2. See, this is taking time because I am making you understand things, but if you know all these points and if you start solving, it takes hardly 2 or 2.5 minutes for you. Okay, but let's see, beta equal to 2, and you have one more equation, alpha plus beta equal to 5, so therefore alpha equal to 3, beta is equal to 2. This is what you know, which means the characteristic polynomial of lambda is equal to lambda square lambda minus 1 whole power alpha, which is 3, lambda plus 2 whole power beta, which is 2. This is the total characteristic equation of the matrix A. Okay, so now we found out the values of alpha and beta. Just to calculate these values of alpha and beta, they have given this condition, because if you apply this concept of rank of the matrix, then that gives you the values of alpha and beta. Now see what they are asking. They are asking rank of A minus I. Fine, A minus I is what you want to identify. So if you want to calculate A minus I, this has eigenvalues as lambda 1 minus 1, lambda 2 minus 1, and so on, lambda 7 minus 1, of course. Okay, now if you have the roots alpha minus 1, the characteristic polynomial of A minus I is going to be roots are minus 1, so ultimately this is the characteristic polynomial of A actually. So lambda plus 1 whole square, lambda plus 1 minus 1 whole cube, lambda plus 1 plus 2 whole square actually. This is the characteristic polynomial of A minus I again. Okay, because ultimately if this is the characteristic polynomial of A, if you solve this, you will get the roots as alpha 1, alpha 2, lambda 1, lambda 2, and so on, lambda 7. So the equation which has lambda 1 minus 1, lambda 2 minus 1 as the roots is nothing but this equation. If you simplify this, lambda plus 1 whole square lambda cube lambda plus the whole square. So here you can see, therefore rank of A minus I is equal to 7 minus, sorry, so 7 minus 3, which is equal to 4. So therefore rank of A minus I is actually equal to 4 actually in this case. Clear to all of you? Yes or no? Now did you understand why I have given you hint yesterday? If you have roots decreasing by 1, then the function should be replaced with f of lambda plus 1 is equal to 0. That's what. Okay, this is what I've given you. If you are increasing the roots by plus k, of course if your roots are changing by k, then x minus k is what the equation should be. So ultimately these are the points where the hint is useful to you. Okay, clear to all of you? Did you all understand this concept of rank which we have discussed in yesterday's class, and this some hint what I've given you for polynomial equations by changing the roots? That's, these 2 points are helpful for you in framing this complete question. Okay, is this clear to all of you? Yes? Did you all enjoy this question? How many of you liked this question? It's a tough question, of course. It's not tough actually if you know this concept of that single formula rank of A is n minus algebraic multiplicity of 0 and a bit of basic knowledge on equations, polynomial equations. It's a easy question to solve, of course. Okay, it took this time almost some 10 minutes or 15 minutes because I have explained it in a detailed sense to you. See what you have done here, same thing you are doing here also. Okay, and just calculations of alpha and beta, that's all. Clear? So anyway, this value is 4 integer, so this is 4, of course. This question was asked in the year when I got all India rank 40 actually. Yeah, some 4 years or 3 years back down the line. Okay, now chalo, let's solve. So in today's class basically we'll talk about vector space and subspaces, and of course also span of a vector space, and we'll go for this solving methods. Okay, and also if time permits I'll also talk about partition matrix and its properties, of course. Okay, so now coming to this vector space. So what is a vector space? You know, basically if people ask you what is a sorry, good evening sir, sorry for interruption. For get DA, should we read vector calculus or single variable calculus? Single variable calculus, Shiva. Only single variable calculus is in the syllabus. I mean you don't have vector calculus in the syllabus, of course. Okay, fine. And of course along with learning basic techniques you should go for a bit of optimization techniques, which I'm going to teach in single variable calculus again. Okay, like we'll have so you have an integration problem for homework, sir. Yeah, of course I've given. Is it for CSE? Vector calculus is not even for CSE also. Okay, for computer science you don't have vector calculus. Basically in a data science course in single variable calculus we talk about optimization techniques. Okay, and in optimization techniques we have this convex optimization, of course, which we'll see then again at that point. So that's the only extra part in single variable calculus. Okay, now see vector space. Okay, before going for vector space, since one of our friend is asking, we'll see one interesting thing. Like in last class I have told you integral 0 to pi by 2 root of 1 minus sine square x dx, which is equal to 1 minus 1, of course. Okay, so this is what we got eventually. Integration of cos x is minus sin x, of course. No, this is plus 1, correct? Yeah, this is plus 1, of course. In yesterday's class I think I have written minus 1. Sorry, if I have written minus 1, please correct it. It's going to plus 1. Okay, because integral 0 to pi by 2 cos x dx is 1. Okay, so this is what you get. Clear? Now I have given you one question. If you have any constant k here, k square, let's say, okay, say I have given k is equal to integral 0 to pi by 2 root of 1 minus k square sine square x dx in bracket k is not equal to 1, or in general 0 less than k less than 1, because I don't want to enter the complex region. So this is what I have given. Okay, now many of you I think have tried this question. Did anyone of you try that integral, calculating that integral? Actually, did anyone of you try calculating that integral? No? Yes. How many of you tried to calculate? I think I have given 0.1 or 0.2, no, maybe some number, but whatever the number I have given you, I might have given definitely something which is between 0 and 1. So did you all try that integral? Now did any one of you get answer for that? 0.2 I have given. Okay, fine, good. So 1 minus 0.2 whole square sine square x, good. Maybe okay, k square sine square x, whatever, you know, you might have done. K is anything somewhere in between this. So Did anyone of you get answer for this? Putting 1 equal to k square sin square x plus sin square cos square 2x. Okay, if you do that, then what happens? Sin square 2x plus k square cos square 2x. Then if you do that, but I failed to solve it, sir. Yeah, of course, I understand. 1.5582 numerical methods. Sagnika, how did you calculate Sagnika? Because you are telling some answer. 1.5582, whatever. You're not able to solve it, right? Majority of you might not be able to solve it analytically, at least. Okay, I think Sagnika, you might have taken help of any integral calculator or double integration you have taken. For what? For this function. See, basically I'll tell you one thing. This integral is not solved analytically. Not solved analytically. Clear? This is not solved analytically. You have to go into series solutions, of course. Okay, see, whatever you do, you might be running in the loop, but many of you might not have been successful in getting the solution, of course. Correct? Try to put 0.2 sin x as y. Yeah, of course, I understand, but you might not have got it, right? See, many of you might have tried this, but again ran into the same loop that you will be ending up again with this integral. Okay, so the main idea here is this is called elliptic integral actually. Okay, elliptic elliptic integral, and these elliptic integrals are solved only numerically. Even if you try any solver, okay, like for example, if I try to solve this using a calculator, Wolfram alpha is one definite integral calculator. If I open, for example, say Wolfram alpha is one of my free tool I keep using always. So I'm just showing you. Okay, I'm just showing you. So if you solve this using Wolfram alpha, if you ask Wolfram alpha to show steps, okay, it cannot solve ultimately because it leads into series solutions of solving. Okay, it leads into series of sin square x and all, and finally what it does is it will truncate at some point and it will show you some truncation errors. Okay, like you can see 0, pi by 2, I'm giving pi by 2. Okay, and here you can see this is not sinus, sqrt square root of, you can see, maybe I'll zoom it. Okay, so you can see square root of 1 minus 0.2 into sin x whole square, 0.2, maybe I think I have given 0.2 into 0.2 into sin x 0.2 into sin x square, then this. Okay, square root of 1 minus 0.2 sin x whole square, yeah, this complete value dx. Okay, so if you click submit, for example, if you try to get the value of this integral, okay, so let's see, it takes some time, of course, to calculate. See, it's taking so much time, of course, in fact. Okay, so 1.5548 is what something Sagnika has told us. 1.5582 is what you have told, so it's numerically coming up to be 1.5549. So you can see this integral is basically a representation of this. E stands for elliptic integral. Actually, see, here it is given, of course. Okay, okay, so E of x, m is elliptic integral of second parameter where m equal to k square, something is given. This 0.2 is actually obtained by 1 by 5 actually. So if you write 1 by 5 square, this is nothing but this 1 by 25. So it is of elliptic integral actually. Okay, and if you ask it to show some steps, okay, so maybe it's not here. Yeah, it's not here, but of course I know the main technique how it's calculated is basically using numerical techniques. Okay, basically Tabs-Odell rule or Simpson's 1/3 or Simpson's 3/8 is used in order to calculate this value 1.55 whatever. Okay, it's not like a very smooth value. You cannot tell it like pi by 8 or pi by 2, something like that. This 1.558 whatever you got is basically this. So in one video you explained for every branch while practicing questions with our branch questions we should follow other branch also, like for CSIT we should follow. Then for DA, as of now no need, because even if you want to follow it, there's only 1 year. You'll have PYQs of only 1 year, but if you want you can follow, it's up to you. Okay, but in linear algebra you have many excess parts in DA, okay, which are not in CS. Clear? So anyway, this is elliptic integral. So how we'll solve this is using numerical methods. Can be evaluated using sorry guys, using numerical methods. Okay, so this is done using numerical methods, of course. Okay, So even though syllabus is mentioned, it is very confusing for DA, so especially math. It's okay, no issues. Okay, we can see. So anyway, so that's the idea. Basically, this integral cannot be done analytically. It's an elliptic integral, and we can calculate it using numerical methods. Done. So let's come back to the vector spaces. So what is a vector space? Okay, why I have taught, why I am inclined to teach this at the last lecture is because it's slightly off track compared to matrices. But again, if you go in depth, then why k equal to 0.2 only? You can take 0.4, doesn't matter. Okay, any value between 0 to 1. Okay, I'm keeping k between 0 to 1 because I want to stay in the real number field. I don't want to enter complex fields. Okay, because the moment k goes beyond 1, 1 minus k square sin square can go beyond 1, of course. Okay, so then I mean it can be negative, so therefore square root of a negative number again jumps into complex plane. So to eliminate that, I have kept 0 to 1. That's it. Okay, clear? Then let's see this vector space. So first of all, you know what is a vector? Magnitude and direction. It has some magnitude as well and direction. Now when you come to the space, okay, 3-dimensional space, a vector V, let's say for example, it is denoted with coordinates x1, x2 and x3. You know, this is a vector which is denoted by the components in which you write it. Then let's see, a space is nothing but vector space. A vector space, say V for example, is the set of vectors which is closed under vector addition and scalar multiplication. Okay, scalar multiplication. So what does basically a vector addition and scalar multiplication tell you? Like, this is basically a set which contains vectors. So let's say you have many vectors which are in this set. The meaning of vector addition is if x comma y belongs to this vector space. Let's say if x and y are two vectors in this set, of course in this space where there are vectors, then ultimately x plus y should be unique. Of course it will be unique, should be unique, and x plus y belongs to this space V again. Okay, which means if you take any two vectors in that set and if you add them, the resultant vector should also lie in that vector space. Okay, got it? And also the second point, scalar multiplication. If x belongs to V, then for a scalar C, of course, Cx should also belongs to this space again. Okay, so C times x should also belongs to that V. Means if you see this, then this set which is set, or generally in theory, because we are dealing in space in general, so we are calling it space. So this space should be in such a way, if you take any two vectors in that space, definitely the resultant of that vector. And how you get resultant? By doing vector addition, correct? You know, in physics you might have studied, if this is vector A and if this is vector B, then ultimately the resultant vector addition is nothing but this vector which is closing. Okay, so C is equal to A plus B. You might have studied this. Okay, so now if you pick two vectors x and y in that space, the summation of that should also lie in the same set again, and also this C should also lie, C times of x should also lie in the V. Okay, so you can understand, in general any linear combination of this will lie in V. Okay, that's what we generally mean by means of these two statements. Okay, and people have developed certain sets. Of course, if you look into the research, people have developed certain sets where sometimes there are few sets which hold this but it failed to hold this. Okay, but it will hold this again, it will fail to hold this. There are some sets in which, of course, some special functions where one of these can get violated. Okay, it's not like always both stay together. People have developed it. Now let's see what is a subspace. So subspace is nothing but, you know, subset again, okay, because V is basically a set which contains some vectors, so a subset of that, okay. So clearly subspace is a space which is a vector space. If I want to call it vector space, again all this vector addition and scalar multiplication should hold, but it is a subset of V. The same thing, okay, the name itself tells you the subspace, okay. It is also a vector space, but it's only a subset, okay, subset of the V, of course. Now why it's familiar or easy to work with subsets, okay, because few times what happens, the vector space consists of many vectors, but when you borrow a subspace from that, this subspace is defined by a less number of vectors than compared to V, but contain all the vectors as that of V. Look, for example, let's say if I ask you these things, I'll tell you one thing. Look here. Let's say for example x comma y belongs to S. Okay, so let's say x comma y belongs to S, for example. Okay, then you take any linear combination that will definitely lie in this S. The reason for that is, look, if x is lying in X, this implies some scalar into X should also lie in S, because this is a vector space. So this vector space should hold scalar multiplication. So if there is a vector in S, then any scalar times multiplication of this X should also lie in the S. Agreed? Yes or no? Correct? Please type in the chat box. If this S is belonging to S, this subspace S, then any scalar multiplication of X should also lie in the S, because this is called a vector space only if this is closed under vector addition and scalar multiplication. So using scalar multiplication, I am showing this too. Yes or no? Please type in the chat box. Everyone. So please type in the chat box. Is this clear or not? Is this clear or not? If you want to call that a vector space, then ultimately if X is element of S, then some scalar times X, which is A into X, should also belong to S. Now similarly, if Y belongs to S, this implies A into Y should, or B into Y, let's say for example, B into Y should also belong to S, of course. Now if I call this AX as some vector, say for example Y, and B or AX as some let AX is equal to some vector B, and okay, B also have used, fine. Then let's say this is maybe F, and BY is G, BY is G, for example. Let's say if I call this G, then you can understand, if this vector, which is nothing but F, is belonging to S, G is also belonging to S, then since F and G are inside S, any linear combination, means basically this F plus G vector addition, this S should obey vector addition. If F and G are inside the set S, then ultimately F plus G should also lie inside set S. Yes or no? Correct? F plus G should also lie inside this S. Correct? Two? Will you all agree? Correct? If F and G are belonging to S, then ultimately F plus G should also belong to S. Then only it's called a vector space. It should be closed under vector addition. Correct? So this implies for F comma G belonging to S, F plus G should also belong to S. That is, AX plus BY should also belong to S, of course. AX plus BY should also belong to S. So that means if there are two vectors in the vector space, then any linear combination should also lie inside the vector space S. Okay. Now using this, what we can write is, let's say if there are 10 vectors inside S. Okay. Out of these 10 vectors, let's say 2 are independent and 8 are depending on each other. Then ultimately you can reduce this 10 vectors into some 3 or 4 vectors, because out of those 2 linearly independent vectors and out of the remaining dependent vectors, since this involves all linear combinations of S, in S we can have lesser number of elements as compared to capital V. Yes or no? V is the total vector space which includes all the linear combinations whatever you have. Then this S can be brought out from V such that this V includes all the elements, and any linear combination of this is also included in S, correct? Now you can see we define one important word which is called span. Span of a vector space, it can be a subspace also, doesn't matter. Space, let's say subspace for example. Span of a subspace, yes, okay. So span of a subspace, yes. So this actually tells you, the word itself tells you span. What is span? Okay, like let's say normally in aerodynamics we use this word wingspan very much. So if I talk about the word span, it is nothing but the spread up to which this set is showing its effect, correct? Means let's say for example, spread of subspace yes, okay, span of subspace yes is nothing but to what extent in a three-dimensional space, for example, let's say if you have a n-dimensional space in general, to what extent or in what particular directions this yes is making its impact, it's occupying, is what given by this span. So span is a set span of S, it's called span of S, let's say W for example. Then this W is basically the set containing all linear combinations of yes, of elements in S, all linear combinations of elements in yes, okay. Now I'll tell you with the help of an example so that you can understand things in a much concrete way. Look, let S is equal to, for example, let's talk about an example, you'll get it. Let S is equal to set of 1 0 0, let's say, and 0 1 0 for example, okay. So let's say these are the two elements in this space, okay. So these are the two elements in this space. Now let's see W. If you calculate span of S, span of S should contain any linear combination. So C1 times 1 0 0 plus C2 times 0 1 0 actually, okay. So this is what span is, okay. So this S contains all the elements which are linear combinations of these two, correct? So which are linear combinations of these two actually. So now this gives you something like set of C1 comma C2 ordered pair, which means this span of S using these two vectors, if you write linear combination of these two vectors, that's nothing but a point on a two-dimensional space, correct? Because you can see these are x coordinates and y coordinates. C1 and C2 can be any two scalars. So if you make this combination C1 and C2, C1 of 1 0 0 plus C2 of 0 1 0, it gives you a ordered pair, okay. And this ordered pair involves a complete two-dimensional plane, yes or no? So the span of S is nothing but 2D plane completely. Means if you give these two vectors with the help of some linear combinations can occupy a complete two-dimensional plane. The span of this set S is nothing but this two-dimensional plane, of course, okay. So span is basically the spread, or basically whatever this region that can be occupied by these vectors with a linear combination is called span. Now normally in gate level and all, what they ask you is, they'll give you a vector, they'll give you a set S of course, and they'll give you one more vector, and they'll ask you whether this vector is within the span of this set S, okay. Let's say for example, if I give you a thing like is 2 3 4 is 2 3 4 in the space spanned by sets 1 0 0 and 0 1 0, let's say, okay. So let's say you have this, then ultimately you know whatever the linear combination you write, 2 3 4 is not equal to C1 1 0 0 plus C2 0 1 0, okay. Whatever the value of constants you take, C1 and C2, you can never write this as linear combination of these two vectors, correct? Which means by the definition of span, this vector 2 3 4 cannot lie in the span generated by these two vectors, correct? Yes or no? Please type in the chat box. I am telling, if I give you this vector and if I ask you is this vector within the span of these two vectors, then ultimately you can see you physically cannot write any linear combination of this vector in terms of these two vectors. Okay, which means in the region spanned by these two vectors, you cannot find this element. Correct? Yes or no? Type in the chat box. Is this clear to all of you? Span is a set which is containing all linear combinations of elements in S. So this element will not be in this span of S. Correct? Okay. Now try to understand one point importantly here. If you cannot write these three vectors, you cannot write this as linear combination of these two, then ultimately this vector is linearly independent. Yes or no? Correct? If this vector is not in the region spanned by these two vectors, then this is linearly independent vector. Correct? Because it cannot be expressed as linear combination. It's not linearly dependent on these two. So ultimately this vector is linearly independent. If this vector is linearly independent, if you take determinant of these three vectors, okay, so this implies linearly independent combination. It's a linearly independent combination. Now if this is linearly independent combination, then ultimately you know how to check linear dependency and independency. That's how whether checking of any vector, checking any vector lying in the span of lying in the span generated by other vectors is same as checking linearly dependent or linearly independency. Okay, did you understand? The presence of an element within the span is same as the vector linearly depending on the other vectors. Ultimately, right? That's what the definition, right? Because the span is nothing but the set containing all linear combinations, and if this cannot be expressed as linear combination, that means this element will not be present in the span. That's it. Okay, so the element lying in the span or not is same as the vectors being linearly dependent or not. Clear? That's the idea. That's why in yesterday's class I have taught you the concept of linear combination. Got it? Okay. So now let's say if I give you three vectors, okay, like this, and if I ask you whether one of them lies in the span of other two, then what you'll do, you'll check whether these three vectors are linearly dependent or not. If they are linearly dependent, then ultimately yes, correct, the vector lies within the span generated by these two. If it is non-zero, then ultimately they are linearly independent and this vector do not lie within the span generated by these two. That's it. Okay, is this clear to all of you? Did you all understand the definition of span and how to check whether a vector is within a vector space or not? Clear? Ultimately if this is not in the span of S, that means this vector is not within this vector space. That's what, right? Is this clear to you or not? Please type in the chat box. Everyone, whoever is on live, please type in the chat box. Is this clear to each and every one of you or not? Clear? If you have any doubts, please ask me kindly. Or else we'll move to the solving techniques. Okay. Clear to each and everyone? Yeah. Okay. So normally they'll ask you whether this vector is in the span or not, whether they are, that means it's equivalent as asking the question whether they are linearly dependent or independent. That's why after defining vector spaces and subspaces, the immediate topic in the syllabus would be linear combinations. Okay, because ultimately checking whether the vector lies in the subspace or not is same as checking linearly dependency or independency. That's what. Okay. Now let's go to some iterative methods. First, let's see some methods to solve a linear system of equations. Okay, so the first thing which I would like to go with is Gauss elimination, which is quite common. Gauss elimination method. Gauss elimination method. Guys, before going for Gauss elimination, I want to ask you one thing. You know direct inversion method, if you have Ax is equal to B, then if A is invertible, you know X is equal to A inverse B. This is direct inverse method. Do you know something called Cramer's method or Cramer's method, of course you can say. Do you know this? Is there anyone who don't know this? If you don't know, then we'll. So when will Dona batch started? Dona is actually the name of the team, okay? The name of the batches is like Sest and Parakam. We have already started, and of course we you know, basically any updates on the new batches will be keep rolling out on the our YouTube channels, of course. Okay, and also if you're following these Telegram channels regularly, then you can get these good idea about these batches and all the things. Okay, and recently today also there is a launch of one of the batches on YouTube, so please go through all these sessions, okay, which could help you. Now is these two methods familiar? If they are familiar, I'll not go because they are just basic methods, but if you are not familiar with this, then we will look at Gauss elimination and all the stuff. So is John Bird higher engineering mathematics is good for concept layer in depth? No, not at the gate level. Okay, normally we have seen John Bird. John Bird is only till maybe some good high school level or PU university level, but not beyond gate. Today one video upload in this channel, I'm asking that batch. That is again I'm telling you, it's just like a promotional video. Again a roll up comes up again for launching of batches. Okay, so please be focusing on these channels. Okay, keep in touch regularly so that you'll get all the updates. Clear? But it can be only for 3x3 method. It can be for 4x4 as well. Okay, but the idea is the determinant, this coefficient matrix should not be singular matrix. For both these methods to finding determinant dx, dy, dz, of course, yeah, two, but in general you can adopt these methods only if this A inverse exists. Okay, means that A is not equal to 0. Only in such case you can use these methods. Okay, there is limitation again, but I hope all of you know this. Okay, this is direct method. You know, if Ax equal to b, then x equal to A inverse b. You'll calculate A inverse, multiply it with b, you'll get x directly. Okay, but this can happen only if A is non-singular, and similarly here this Kramers rule is also applicable only if the determinant of the matrix is non-singular. Correct? Because otherwise if the determinant is singular, then you'll have zeros in the denominator which couldn't solve your system. Two. So anyway, these are some basic stuff which you might have learned. Then coming to Gauss elimination method. So what we do in a Gauss elimination method, Ax is equal to b is what you have, of course. So we generate augmented matrix. I've told you doing rank calculations how to calculate augmented matrix. We generate augmented matrix. Okay, so we generate augmented matrix. So when you generate this augmented matrix, you have A11, A12, A13, B1, A21, A22, A23, B2, A31, A32, A33, and B3, of course. Okay, so you have this. Then let's see, basically the system what I am taking is A11x plus A12y plus A13z is equal to B1. Okay, then A21x, this is stuff we write every time, plus A23z is equal to B2, and A31x plus A32y plus A33z is equal to B3, of course. Okay, then you can see this can ultimately return of the form Ax is equal to b, where this A is A11, A12, A13. This is all pretty fun stuff which we keep writing up all the times. A23, A31, A32, A33, of course. Then x, y, z is equal to b1, b2, b3. Okay, so this is the system that you have. Now if that's the system, ultimately the augmented matrix is this. Now what we do is, by performing certain row transformations, we'll try to get this in the echelon form. Okay, so by row transformations, please keep in mind only by row transformations. Okay, by row transformations. Clear? You may have a doubt, why not column transformations? Okay, because recently I think one of you are asking me. People may have a doubt, why you cannot perform column transformations. The reason is, if you perform column transformations, these equations will get disturbed. Okay, ultimately whatever the technique you follow, you should only try to solve this set of equations. Okay, it's not like you should change the equations. Clear? If you are performing row transformations, maybe multiplying this by 2. Let's say if I say multiplying second row by 2, that means multiplying this second equation with 2. That doesn't change the set of equations. Okay, or if I swap these two rows, for example, let's say first and third row I am swapping. That means I'm swapping first and third equation. That also doesn't change my system of equations. But if I apply column transformations, let's say if I change this C2 and C3, these coefficients will change. That means these equations are not the same. Yes or no? Let's say for example, if I replace this element here and this element here, then this equation is changed. Okay, so equation should not be changed. That's why we should not use column transformations. Clear to all of you? Yes, Ajay, Vasishta, me, Rathod, Alex, Ritik, Sagnika, Prakasam, and lot many names, of course. Did you understand why you should perform only row transformations but not column transformations? Clear to to all of you? Yeah. Now let's see. If you perform our transformations, we convert A augmented B to row echelon form, and we do backward sweeping, and we do backward substitution is what we can do generally. Backward substitution, clear? Backward substitution. Okay, so we do backward substitution basically, and also we apply column operation, then we don't get upper or lower triangular matrix. See, even if you get lower or upper triangular matrix, it's you know, the next case, but the first thing is you should not change the set of equations. Okay, that's what. Now let's see here. If you calculate, so you'll do backward sweeping. How you do? Let us see. For example, let's say for x equal to 1, I'm just taking one system, y equal to 2, z equal to 3. Let us generate a system, okay, and we'll solve the system using this Gauss elimination technique, and we'll check whether this Gauss elimination works or not. Okay, so the first equation which I would like to generate is x minus y plus z is equal to how much it is? 1 minus 2 minus 1 plus 3. So this is 2. Okay, then 2x plus y minus z, let's take for example. Okay, so 2x plus y minus z is how much? 2 plus 2, 4, 4 minus 3, 1. Then x minus 2y plus 3z, let's say some elements I'm taking. 1 minus 4 minus 3 plus 9 is 6. So let's say this is the set of equations I have, for example. Okay, I'm doing with 3 by 3 so that the job is easy to explain. Now if this is a 3 by 3 set of equations, similarly you can follow this Gauss elimination for any size, any number of unknowns. Okay, now if you take this 3 by 3, and I know for this system if you solve, you will get this solution because I have framed these equations based on that solution. Okay, now let's apply Gauss elimination technique. So this implies 1 minus 1 1, 2 1 minus 1 1 minus 2 3. Okay, this multiplied with x y z is equal to 2 1 6. Okay, so these are the elements, and ultimately this is of the form A x is equal to b. Now let's write A augmented B, augmented matrix, you write. Okay, so A augmented with B gives me something like 1 minus 1 1 2 1 6 of course, then 2 1 minus 1 1 minus 2 3. This is what you have. Clear? So if this is what you have, then I've told you by performing our transformations you should convert this to echelon form, and I have shown you how to convert to echelon form. Okay, when we are doing the concept of rank, we have explained you. If you want to convert this to echelon form, first you should make these two elements zeros. So let's say I'm performing R2 changes to R2 minus 2R1 and R3 changes to R3 minus R1. So if you perform these transformations, it leads you to the system A augmented B is equivalent to, let's see, so first term doesn't get changed, 1 minus 1 1 2 of course, then 2 minus 2 times of 1 0, 1 minus 2 times of minus 1. Okay, 1 minus 2 times of minus 1 which is 3, minus 1 times 2 times of this 1 is minus 3 of course. Okay, then last row 1 minus 1 0, minus 2 minus of minus 1 which is minus 1, then 3 minus 1 2, then this is 1 minus 2 times of 2 which is minus 3 of course. Okay, and 6 minus 2 4. This is what you have. Clear? So this is the matrix. Now what we can do is, so while finding rank, can we swap those? Yes, we can swap, no issues. Okay, but you should swap only for getting the echelon form. Okay, because there is some restriction, right? Number of zeros before the first non-zero element. So we will swap only in case of necessity. Clear? Otherwise it will again increase the number of calculations. Now let's see. This is what you have. Now ultimately it's not in echelon form, so we'll make this element also 0 using second row. So R3 changes to, if you apply this transformation again, R3 changes to, or maybe I'll do it here so that you can get some idea. R3 changes to 3 times of R3 plus R2. So let's say you make this transformation. So if you make this transformation, ultimately this element becomes 0. Okay, so by performing this, your augmentation becomes, will be equivalent to 1 minus 1 1 2 0 3 minus 3 minus 3. Then after what you have 0, because 3 R3 plus R2, 3 times of 0 plus 0, it is 0, minus 3 plus 3, 0, then 6 minus 3, 2 3s are 6, 6 minus 3 will give you a 3 of course, and 12 plus 3, 12 minus 3 is 9. This is 12 minus 3, which is 9. Okay, this is what you got, and clearly this matrix is in augmented matrix form. Okay, now, and it's in row echelon form basically. So if this matrix is in row echelon form, then if you convert this into system of equations, the system of equations you get is therefore x minus y plus z is equal to 2, 3y minus 3z is equal to minus 3, 3z is equal to 9. This is what you'll get, correct? To this matrix has got converted. Of course, this if you write back in the form of equations, because whatever we have done only for rows. So this equations is same as this equations again by performing some transformations is what we have. Okay, basically what this tells you, equation 2 is equal to equation 2 minus 2 times of equation 1. That's it. Okay, that doesn't change the system of equations. So by performing these transformations, you have ended up with a system. Now we have converted to echelon form. Now let's see what we do backward substitution. So if you start from the bottom row, okay, so you start from the bottom row and you start going back till the first row. If you look at the last equation, z is equal to 3. Okay, so you will get the variable z equal to 3, and of course this is 2 because we have framed this set based on z equal to 3. Now since you got z equal to 3, you can replace this z equal to 3 here and you can get the value of y. Okay, now since you have the value of y and you have the value of z, you can keep in the first equation and you can get the value of x. Like this, in general, if you have n unknowns, in the last step you will get nth unknown, then using this nth unknown in the n minus 1th equation, you will get n minus 1 unknown, and similarly by repeating the loop you will finally get all the unknowns. That's how you will calculate this vector x actually. Clear? Is the idea clear to all of you? How we are going to perform this Gauss elimination? Yes or no? Please type in the chat box. Is this clear to all of you? How you are going to perform this Gauss elimination? Okay, so here you got 3. So if you put z equal to 3, this implies 3y is equal to minus 9. This is minus 3. So 9 minus 3 is 6. So y is equal to 2 of course. So if you put y equal to 2 and z equal to 3, this gives you x equal to 1. That's it. Okay. Yeah, of course, you should get x equal to 1, y equal to 2, z equal to 3 because we have formed these equations by taking x equal to 1, y equal to 2, z equal to 3. So when you solve this system, this has a solution like this. Clear to all of you? And you can ask me, like, let's say for example here you got 0, okay, and here there is non-zero element. Let's say here you got 0 and here you have non-zero, then just swap these two rows. That's simple as a job. Okay, so like that, this Gauss elimination technique is again very powerful technique to solve the system of equations. Okay, but when you go for sparse systems, we'll see later what is a sparse system and all, but this is how you apply Gauss elimination. Okay, now based on this Gauss elimination, there is one more technique which we can generate, which is LU decomposition technique. LU decomposition. Okay, so what is this LU decomposition? Let's check it up. How we actually proceed to get the LU decomposition basically, and without even calculating inverse, like how we have done in the Gauss elimination without doing inverse of the matrix. So similarly here also we come across the certain multiplication operations which could give us the solution. Okay, so let A x is equal to b is the system. Okay, this is our system of equations. System of equations. Now what you'll get is, look here, we take A is equal to product of two matrices L and U. That's why it's called LU decomposition. We divide this A into two parts, which is L into U, where L is lower triangular matrix, where L is lower triangular matrix and U is going to be upper triangular matrix. Okay, so this is upper triangular matrix of course. Now this is L is lower triangular and U is upper triangular matrix. Actually you can understand this. Therefore Ax is equal to B. This implies LU multiplied with x is equal to b. This is what you will get, correct? Now what we can do is, since matrix multiplication is associative, instead of doing this LU, I can write instead of doing this LU, I can write UX and then you multiply it with L, because multiplication of 3 matrices. X is also a column vector, okay, so it's a matrix. So L UX multiplication can be done in any way. So let UX is equal to Y, for example, okay. So UX is equal to Y. So let's say you have the n by n matrix initially, then you have a n by 1 which is unknowns. So let's say this is A11, A12 and so on, A1n. Similarly AN1, ANN you have, and this matrix is like x1, x2 and so on, xn. These are the unknowns, is equal to say B1, B2 and so on, Bn of course. This is also an n by 1 matrix, okay. So when you have this, then this Ux is equal to Y. So this U is actually a upper triangular matrix, which means all the lower diagonal elements are zeros. So Ux is equal to Y is what we are taking. If Ux is equal to Y, it's a vector. So therefore L times Y is equal to B. This is what you have, okay. So L times Y is equal to B. So Gauss-Jordan is also similar like this. Yeah, we'll see, okay. So this Ly is equal to B, of course. Now when you have this Ly is equal to B, let's understand Ly is equal to B, of course. This L into Y. So what is L? L is lower triangular matrix. If you observe here one thing, this is an upper triangular matrix because these elements are zeros. So in order to get the solution, you have done backward substitution, okay. So you started at the bottom, last row, and you have done backward sweeping so that you got all the unknowns. Now let's suppose, for example, if this matrix would have been lower triangular matrix, okay, which means all the upper triangular elements are zeros, but lower triangular elements you have some elements, let's say. Then instead of doing backward sweeping, to get the values, you would have done forward sweeping. Yes or no? You would have started at first row because these two elements are zeros. You'll get the value of x first, okay. Then after you can do forward sweeping, you will get all the unknowns. So whenever you have this upper triangular matrix multiplied with one vector is equal to some B, to get these elements inside the vector, you should do forward sweeping, correct? So which means if you have the matrix like let's say 1 L maybe like L12 L13, this is a lower triangular matrix, so upper diagonal elements are zeros maybe. So this is L, correct? So 1 0 0, say L21 1 0, L31 L32 maybe 1 if you have, times Y1 Y2 Y3 is equal to B1 B2 and B3, of course. So if you have this, then when you perform this forward sweeping by forward substitution, you can say, otherwise forward substitution, by forward substitution Y can be calculated, correct? Yes or no? Y can be calculated to yes or no? Please type in the chat box. Can I say this? Y can actually be calculated using this, correct? Did you understand? Basically, when whenever you are having lower triangular matrix is that particular matrix where upper diagonal elements are zeros. If you have upper diagonal elements as zeros, then by doing forward substitution, starting with the first row till you reach the last row, you can calculate what are the elements of Y, of course. So this Y can be calculated, correct? Yeah. So if Y can be calculated, then the job is easy. So this Y can be calculated. So if Y is known, then ultimately, you know, Ux is equal to Y. This is exactly like this, okay. So this is an upper triangular matrix. Upper triangular matrix multiplied with X is equal to some constant vector. So ultimately, if Ux is equal to Y, by backward sweeping again, or by backward substitution, you can say, by backward substitution, we can get X. You can calculate what is X. That's it, okay. And if X is known, that's the story. That's what you want. Actually, X can be calculated for the system of equations. Clear? Yes or no? Is this points clear to all of you or not? Please type in the chat box. Yeah, okay. Just a minute, I'll have water. Is this clear to each and everyone? How we are adopting this technique? We are decomposing this matrix. Decompositions are always powerful, okay. Like in yesterday's case, you have seen basically we have decomposed A into PD P inverse. Okay, so diagonalization is also nothing but a decomposition into P D P inverse. So when you decompose anything, then solutions can be obtained without calculating inverse and all. Okay, so that's why it's really nice thing. Okay, now let's see what we have. Let's work out the same example. Let me take the same example to see whether we'll get the solution or not. Okay, we have to do. So let's see. Example, you have x, what is the system? Basically x minus y plus z is equal to 2, x minus y plus z is equal to 2, 2x plus y minus z is equal to 1, 2x plus y minus z is equal to 1, of course, and what we have, x minus 2y plus 3z is equal to 6. Okay, you got these things. Now when you have this, we have to split this A into LU, of course. Now there are two things, or basically there are two methods in which you can split. Okay, so one is called Doolittle's and the other is the 𝐿 algorithm, of course. So let's see, this is nothing but 1 minus 1 1, 2 1 minus 1 1 minus 2 3, of course. Okay, this multiplied with x y z is equal to 216, you know this. Okay, so this is 216. Now if you want to convert this A into LU, let's maybe put the block here so that you can understand. If you want to write this A as LU, of course, this is L, which is lower triangular matrix, and U is the upper triangular matrix. We can adjust this as two methods. Basically, I'll move this slightly here. How you can do this is, A can be written as L11 0 0, L21 L22 0, L31 L32 L33, let's say, multiplied with the upper triangular matrix is U11 U12 U13 0 U22 U23 0 0 U23, of course. Okay, U3 is what you get. Okay, so this is what you have. So ultimately, clearly it's a lower triangular matrix and this is the upper triangular matrix. Okay, now in Doolittle's algorithm, basically Doolittle is one technique to start the things. Doolittle, it's Doolittle, not Doolittle, Doolittle's algorithm. So in Doolittle's algorithm, what we do is, we take these elements L11 L22 L33 is equal to 1. That's what we can do, because it can actually, yeah, fabulous, fantastic. Okay, thank you. But look here, yeah, the main idea is solving the things. Yeah, in Doolittle's, what we can do is, we can fix this lower diagonal elements of lower triangular matrix to be 1, because if you can fix this one, ultimately, see, anyhow you have to calculate total 1. This is 1 2 3, total 6 elements and 6 elements, total 12 elements is what you have to calculate. Okay, but these 12, out of these 12 elements, these diagonal elements are dependent. Okay, means depending on what the values you keep here, these values can be changed. So anyhow you have to calculate this either these elements or these elements. So for simplicity, what we can do is, in one of the matrices you can take diagonal elements to be 1, so that it can reduce the job slightly. Okay, so in Doolittle's algorithm, this is what you'll do, and in 𝐿 algorithm, basically have 𝐿's algorithm, you can just check it up. So in this, we take the upper diagonal elements, the diagonal elements of upper triangular matrices to be 1. Okay, you can follow any of these techniques, and in gate examination, of course, people generally ask you for, whenever the LU decomposition questions are very rare because it's slightly calculative. So if they ask you to do Doolittle, you can, I like your hairstyle. Oh, fine, good. Look here. So you can see, if they ask you to do Doolittle, you can pick these elements to be 1s, of course. Okay. And if they ask you for 𝐿's, you can take these upper triangular elements to be 1s actually. Okay, so the only difference is by choosing in which matrix you have to replace diagonal elements with 1. Okay, in general, if they don't mention anything, you can go with Doolittle's actually. Clear? So let's say I'm following Doolittle algorithm. For example, I'm following Doolittle algorithm. So if I follow this Doolittle algorithm, then what I can do is, okay, what we can do is again, so see here, A is equal to 1 0 0, L21 1 0, L31 L32 1. This is what we have, okay, multiplied with U11 U12 U13 0 U22 U23 0 U33. Okay, so this is what you have. Clear? Now ultimately when you multiply these two, so these kind of methods will also be asked in GATE, sir. They can ask, okay, how they'll ask is, look, they'll give you this system, they'll tell you if A is decomposed into L and U, what is the value of the element U23? They can ask this, okay, which you can get just by multiplying things, okay, but they can ask you these kind of things. You should know how to split the matrix into a product of L and U, okay, that's why. Clear? Now let's see, so if you calculate this elements, okay, how you are going to get that. So let's see, therefore A, what is the element matrix A? Of course 1 minus 1 1, 1 minus 1 1, 2 1 minus 1, 1 minus 2 3 is what we have taken. So this has to be equal to, look, this is very important step, this is the step which is most important. You have to be little careful when you are doing this. If you multiply this L with this U, and if I adopt Doolittle's algorithm where I have taken these elements 1, then let's see how you get. If you want first column element, 1 into U11, 0 into 0, 0 into 0. So the first element is going to be U11. Similarly here, let us make this straight first of all, okay, U11, similarly you will get U12, similarly you will get U13 actually here, okay. So this is what you will get, because if you want to calculate the first row completely, okay, so if you want to, just a minute guys, okay, fine, no issue, sorry, some important calls these people doing, fine, what we're talking, yeah. So if you multiply these two elements, these two matrices, if you want to get the first row, ultimately you should multiply with this first row with first column, first row with second column, first row with third column, okay. Since these two elements are zeros, 1 into U11 gives U11, similarly 1 into U12 gives U12, 1 into U13 gives U13, okay. Now coming back to L21, if you multiply this, L21 U11, this is the element that you have here, L21 U11 plus 1 into 0 plus 0 into 0, second row second column, so L21 U12 U12 plus this 1 into U22, U22 is what you get. Similarly you will have L21 U13 plus 1 into U22 is what you get, 1 into U23, so this is U23 is what you will have, correct, because this 1 into U23 plus 0 into U33, that's the elements. Then L31 into U11, L31 into U11, okay. Then after L31 into U12, L31 U12 plus L32 U22, this is what you will get, correct, because L32 into U22 plus 1 into 0 gives 0. Then for the last element you have L31 U13 plus L32 U23 plus U33, this is what you have finally, correct. This is how you have the multiplication of L and U, okay. Now ultimately these two matrices are equal, so if these two are equal, then definitely you should know how you can calculate L and U, of course, okay. So let's look here. If you simplify, ultimately these two matrices are equal, so this is 1, this is minus 1, and this is again 1, of course, okay. So 1 minus 1 1. Now you can see L21 U11 is equal to 2, because corresponding elements has to be same, so this element has to be equal to this, but you know U11 value is 1, of course, so L21 is equal to 2, okay. So L21 is equal to 2, so you know this is 2, this is 2. Now let's see, L21 U12 plus U22, this element is equal to 1 again, okay. And clearly you can see this L21, it's just a bit of playing. L21 is 2 because you have calculated this here, U12 is minus 1, so this tells you U22 is equal to minus 2, this is 1, so this is 3, of course, okay. So U22 is equal to t. It's slightly calculative. That's why many times in GATE exam only once or twice this question has come up. So I'm just put it in the last lectures. Then again, you can see L21 U1t plus U2t, second or third column, is equal to -1. So ultimately again, L21 is actually L21 is 2, U1t is 1. So this implies U2t is equal to -3, of course. Okay, so this is -3. U2t is equal to -3. Similarly, let's calculate other elements. L31 U11 is equal to 1, and this L31 is how much? Okay, this is not L31. U11 is actually 1. So this tells you L31 is of course 1. Okay, so L31 is equal to 1 actually. Coming here, L31 U12 plus L32 U22 is equal to how much? This is -2. -2. So if you try to simplify, this L31 you have calculated 1, U12 -1 we have again calculated, L32 you don't know, U22 is 3. So if you simplify, L32 is equal to, this is -1. So if you put this -1 to the other side, -2 plus 1 -1. So L32 is -1 divided by 3. This is what we have. Okay, so L32 is equal to -1 by 3. Come back here, last element, L31 U13 plus L32 U23. This is a bit of fun stuff is what I am doing. You can so this is 3. So let's see, this is the 3 of course. Okay, then let's substitute L31. So what is L31? 1. U13, this is also 1. L32 -1/3, U23, this is -3, plus U33 is equal to 3 of course. Okay, minus gets cancelled. This is 1. So 1 plus 1 2. So 3 minus 2 is 1. So U33 is equal to 1 actually here. Okay, so this is what you have the matrix. So you got all the elements. So that means you can see, therefore A is equal to lower triangular matrix. First of all, since we have used Doolittle's 1 0 0, L21. So what is L21? L21 is actually 2. So 2 1 0. Then L31, L32 1. This is my lower triangular matrix multiplied by upper triangular. U11, U12, U13, 1 minus 1 1 of course. Then 0, U22 3, U23 -3, 0 0, U33 is 1. This is how we have the LU decomposition for this matrix. Did you understand how we'll calculate the LU? Elements in L and elements in U, of course both the matrices L and U, so that this multiplication of L and U gives you A again. Clear? Yes, so please type in the chat box. Is that clear to all of you? By performing this simple calculation, see, it is just laborious but need not be, it's not a very complicated operation to do. It's a very simple operation. Okay, and in fact for doing this LU decomposition, if you write an algorithm, it takes only 2 lines. Okay, you can generate pseudocode and you can do the things. Clear to all of you? So once you calculate these 2 matrices, then whatever I have told you, because in this technique, to follow this technique, the only thing you don't know is what are these elements. Okay, if you know these elements, you know these elements because equations are given. Ultimately B is known, B1 B2 B3 is known. These elements are now calculated, so you can calculate these elements. Okay, now if you put it here, since U is known, X is not known but Y is known, you can calculate X. That's it. Okay, so this is how you calculate LU decompositions actually. Clear? Okay, now let's see. We okay, so this is clear to all of you. I hope it's clear. Okay, just a minute, I'll have water. So fine. Okay, so see here, next methods which will go is actually, one method is, which is of course of faster convergence, Gauss-Seidel method. Gauss-Seidel method. Okay, so Gauss-Seidel method. So what is this Gauss-Seidel method? Let's see. We actually will have this system, of course. When you have the system like A x1 a11 x plus a12 y, or maybe let's say I'll slightly modify this system. We'll take a11 x1 a12 x2 plus a13 x3 is equal to b1. Okay, then a21 x1 plus a22 x2 plus a23 x3 is equal to b2, and a31 x1 plus a32 x2 plus a33 x3 is equal to b3, of course. Okay, so this is what we have as a linear system. Now if you want to solve this system, of course, okay, this is basically a numerical technique which generally I thought of teaching in numerical methods, but since some of the CS and DA guys won't come there, so I'm teaching it here. So I'm just telling you one thing. There is something called diagonal dominance. Okay, so Gauss-Seidel, see, if the system is not diagonally dominant, still the system can be converged, but the convergence in Gauss-Seidel is guaranteed always if your system is diagonally dominant. Okay, so convergence is guaranteed. Convergence means a solution, coming up to a solution is guaranteed. Convergence is guaranteed for a diagonally dominant system. Diagonally dominant system. Okay, convergence is guaranteed for a diagonally dominant system. So what's a diagonally dominant system? That's the main thing we have to know now. So diagonally dominant system. What does this diagonal dominance tells you, of course. Okay, now if you convert this to matrix form, you will have a11 a12 a13 a21 a22 a23 a31 a32 and a33, of course. So this multiplied with x1 x2 x3 is equal to b1 b2 b3. So let's see what we have. See, I'm telling you, diagonal dominant system has definitely convergence. Okay, but for convergence to exist, the system need not be a diagonally dominant system. Okay, so what is this diagonally dominance word? First of all, I'll tell you. Look, if you for example take this row, take these elements, this is the diagonal, correct? So this is the principal diagonal of this matrix, coefficient matrix. So diagonal dominance implies magnitude of a11 should be definitely greater than or equal to magnitude of a12 plus magnitude of a13. Similarly, magnitude of a22 is greater than or equal to a21 plus a23. Similarly, a33 should be greater than or equal to a31 plus a32, of course. This is called diagonally dominance. I'm repeating, if you have a diagonally dominant system, definitely it gives you convergence, but for convergence to exist, the system need not be diagonally dominant. Understood? Okay, there are few systems, a few general systems for which Gauss-Seidel method works. Again, Gauss-Seidel method do not work also. Okay, but if the system is diagonally dominant, then 100% you'll get convergence. That's what we mean. Okay, I'm telling you. Note, I'm getting a note here. For the system to have convergence with Gauss-Seidel, to have convergence with Gauss-Seidel, it need not be mandatorily diagonally dominant. Diagonally dominant. It need not be mandatorily diagonally dominant. Like normally when we are doing computational fluid dynamics, okay, so again I'm just slightly jumping the things, but if you see when we are doing about CFD, okay, we come across some systems where things are not diagonally dominant, but still Gauss-Seidel works for that systems. Okay, we have seen it many times. Okay, normally when we are researching in fluid mechanics and all, when we are talking about a bit of discretization techniques, which is again beyond the scope, This is what statement we'll observe 100%. Okay, but since everyone want to have an assurance that, let's say for example, if I'm putting some effort, I'm writing some code, I'm trying to solve a system. After doing all this business, let's say for example, if I'm not getting solution, it's like a time waste, okay, and lot of effort waste. So before we start something, we will try to throw the things into diagonally dominant systems so that we can get solution. Okay, so we'll see what is the system. First of all, this point is very important. Okay, note. But since we always need to have a guarantee for the solution, we convert the system into diagonally dominant systems. Okay, so how do we do that? Just by swapping the equations. Let's say for example, in this form we are not getting diagonal dominance. Okay, then what we'll do, we'll swap some equations and we'll see whether we are getting diagonal dominance or not. Okay, that's what. Now if you look at the system, what I have and how we actually follow the process, let's see. Let a11 x1 plus a12 x2 plus a13 x3 is equal to b1, a21 x1 plus a22 x2 plus a23 x3 is b2, and a31 x1 plus a32 x2 plus a33 x3 is equal to b3. Of course, is a diagonally dominant system. For example, is a diagonally dominant system, is a diagonally dominant system. Okay, so this is a diagonally dominant system. Then let's see what you have. From first equation, this implies x1 is equal to 1 by a11 into b1 minus a12 x2 minus a13 x3. This is what we get, correct? Then x2 is equal to, from the second equation, if this is diagonally dominant, it is set in such a way that the system is diagonally dominant, then 1 by a22 into b2 minus a21 x1 minus a23 x3. Okay, and similarly x3 is equal to 1 by a33 b3 minus a31 x1 minus a33 x2, sorry, a32 x2. This is what we have. Clear? This is the thing. Now first of all, if you want to calculate this x1, you should know what is this x2 and x3, correct? Yes or no? This is the iterative technique that we are going to follow. So this is iteration scheme that we are following. You know, iteration means basically we'll repeat the same thing again and again, but of course for the different story. So look for the different values. If you want to calculate this x1 initially, you should know what is this x2 and x3, correct? But we don't know. So what we'll do is we'll start with some initial guess. Okay, so we start with initial guess. Okay, so we start with initial guess. X1 is equal to say x1 naught, x2 naught, and x3 naught. Okay, so this is in the 0th guess. Okay, 0th guess is basically, so only making diagonal dominant makes calculations easy. Yes, making calculations easy is something separate, but it assures a solution. Okay, that's why something we'll get some solution out of the system which is physically fitting the given system. Okay, that's why diagonal dominance is always important, because it assures some mathematical solution for you. That's what. Okay, now coming here, since we don't know how to start, we'll choose some initial guess. This subscripts are basically for the unknowns x1, x2 and x3. Superscript is basically the number of iteration value. Okay, when I solve the question, you'll make it it'll get more clear. Since these are the initial guesses, I'm putting the subscript zeros, and in general the solution is such a way that x1 I plus 1 is equal to xi, and this is ith step. x2 I plus 1 is equal to, now since when you are performing this calculation, you have already calculated this x1, you will update this value immediately, and this, since you haven't calculated, you will use only I. When you are calculating the third unknown, ultimately since you have calculated these two unknowns in this I plus 1s, you have this updated values, you will use this updated values actually. Okay, these are the steps and I starts from 1. In the first iteration you will have the values, in the second iteration you will have the values. Then there comes a convergence where if you check this value of x1 in the I plus 1 and in the ith iteration, there won't be much difference. Okay, then we say the solution got fixed, and that's the solution. Of course, like I'll use the same example, same set of equations, and we'll apply this technique, and we will see how to work out with Gauss-Seidel, which actually assures a solution. Okay, so let's see how we are going to do. Example, the set of equations what we have is, what are the equations we have? So x minus y plus z is equal to 2. X minus y plus z is equal to 2. So let's say, for example, for making diagonal dominant, x minus y plus z is equal to, x minus y plus z is equal to 2 minus 2, 0. So this is 3. Okay, I'm setting a diagonal dominant system intentionally because I want you to show a solution. Then after, 2x plus y minus z is equal to 3. That's what I have taken. 2x minus y plus z. 2x minus y plus z is equal to 3 is what we're getting. Okay, fine. So let's define a diagonal dominant system, for example. So x plus 3y minus z, let's take for example. So 1 plus 6, 7, 7 minus 3 is 4. Okay, and maybe the other system is the last equation what we have done. Okay, x minus y plus 3z, let's take. Okay, so x minus y plus 3z is equal to 1 minus 2 minus 1 minus 1 plus 9 is 8. Okay, so this is the system that we have. Now let's apply Gauss-Seidel for this technique, and let's see. So first of all, it is a diagonally dominant system. This system is diagonally dominant, of course. Diagonally dominant system. Okay, so this is a diagonally dominant system. Now if this is diagonally dominant system, then you can write from the first equation, this implies x is equal to 1 by 2 times of 3 plus y minus z. This is what you get. Okay, then from the second equation, y is equal to 1/3 times 4 minus x plus z. This is what you have. In the third equation, z is equal to 1 by 3 times, again 1 by 3 times 8 minus x plus y. This is what you get. Okay, now this are the things what you have. So let's see, if you want to perform iterations in the ith plus 1th iteration, since you don't know what are the values of these two, we'll use the ith iteration values. For the I plus 1th iteration in y, since you have updated this x, we'll use the I plus 1th value, and here since you haven't updated yet, we'll use this. For the I plus 1th value here, since you have updated both by this time, this is how we have the iterations. Okay, so because to calculate this step, you don't know what are the y and z values, so what are in the previous steps we'll use. But when you are calculating this y, since this x is already updated value which you have found out, you will use that x as updated value, and z you'll use the previous value because you haven't updated. In this z, since you have these updated values of both x and y, you are going to use this x and y. So let's see how we will start this iteration. Look, we have to make an initial guess. Let initial guess be 0, 0, 0. This is x1 in the 0th iteration, which is the guess value, or maybe you can start with 1, 1, 1. The calculations will be simple. So should be 1, 1, 1. Let's take. Okay, so that means we have taken x1 initial guess is 1, x2 initial guess is 1, x3 initial guess is also 1, of course. Okay, so we have taken 1, 1, 1 initial solutions. Now let's see first iteration. Let us perform the first iteration for I is equal to 1. Okay, excuse me, sorry. So see here, for I is equal to 1. Let's see, first iteration is what I am doing. Now when you perform this first iteration, let's see what you get. If you put I equal to 1 in these equations, what you will get? X after the first iteration is equal to 1 by 2 times 3 plus, okay, 3 plus y. If you put I equal to 1, sorry, if you put I equal to 0, actually, if you put I is equal to 0, for I equal to 0, actually, okay, first iteration for I equal to 0, x1 is equal to 1 by 2 times of 3 y of 0. Sorry, these are also zeros. These are the initial guesses we have taken. Okay, so these are the initial guess. So if those are the initial guesses, okay, then if you put I equal to 0 in this equation, x in the first iteration, x1 means x in the first iteration is equal to 1 by 2 times 3 plus y of 0 minus z of 0 actually here. Okay, y of 0 minus z of 0. So if you put x equal to 1 and y equal to 1, ultimately this is 1 and this is 1. So this gives you how much? 3, 1 1 gets cancelled. So this is 3 by 2, which is 1.5. Okay, so this is 1.5. Then x, first of you have completed. Then again if you put I equal to 0 in this, y in the 1 is equal to 1 by 3 times 4 minus, if you put I equal to 0, this is x1 plus z in the 0th iteration. This is what we have. Okay, now clearly you can see x1 is 1.5 because we have calculated just now, it's 1.5, and z0 is 1 again. So if you simplify this, 4 plus 1 5, 5 minus 1.5 is 3.5, 3.5 divided by 3 is how much? 3.5 divided by 3, 3.5 by 3, 1.1667, 1.1667. Okay, so let's say for 4 decimals we are wrapping up. And z in the first iteration, again if you put I equal to 0, 1 by 3 times of 8 minus x in the first iteration, because we have already done, plus y in the first iteration. Now let's see what are these values. If you keep these values, this x in the first iteration 1.5, y in the first iteration 1.1667. Okay, so if you simplify this, let's see what you get. This value minus 1.5 minus 1.5 plus 8 plus 8, this value divided by 3, so 2.555 is what you got. Okay, these are the first iteration values. Therefore you got x1 is equal to 1.5, y1 is equal to 1.1667, and z of 1 is equal to 2.555 actually. Okay, these are the values you got. Now when you perform the second iteration for I equal to 1, again the same story. This whatever we have done, the calculations, same we have to repeat once again. Now what kind of question they'll ask you in gate examination? They'll ask you, this is my diagonal dominant system. Okay, I have started with initial guess. They'll give you these values. Okay, initial guess is what they given. The value of x2 after first iteration is dash this value. Okay, did you understand how questions can come in gate examination? They'll give you a diagonal dominant system. They'll tell you they're solving using Gauss-Seidel, and they have given you initial guess. Okay, they have given you initial guess. They'll tell you for initial values of x equal to this, y equal to this, and z equal to this, the value of y after first iteration is dash. They can ask you for 1 mark. The value of z after second iteration they'll give you. Okay, that's what. So initial guess must be 0 0 0, then so they can satisfy any equation. Need not be. Okay, you can take any initial guess. Clear? Initial guess, there is no restriction on it. That's what, na, guess. You can guess whatever you want. Okay, but if you are guessing the things very close, then the solution converges fast. Okay, so what happens is for I equal to 1, then x2, y2, z2 values you'll get. Okay, by doing this successive calculations. Okay, so at one point what happens is, let's say for example after 4 or 5 iterations, what happened? x4 value and x5 value will be very close to each other. y4 and y5 will be very close. z4 and z5 will be very close. At that point, even if you are performing iterations, only the last decimals will change. Then you can understand that's the solution. Clear? After some points, what happened? Like for example, you see this value is 1, this is 1.5, there is difference. 1, 1.16, 1, 2.55. There is big difference between these two. Let's say if you perform 1 more iterations, what happened? x2 value and x1 value can, maybe they can come very close. Okay, similarly y2 y1, z2 z1 can become very close. So there comes after 3-4 iterations, the values between the xyz in that iterations and the previous iterations are not very much different. Okay, so the difference dies down slowly and you will achieve a solution. Let's see what all we get. Okay, maybe if I had a connection with MS Excel I would have shown you, but it's okay, we'll see. Gauss-Seidel calculator, we'll see if there is one calculator maybe for that, because nowadays we have you know, lot of stuff on internet. We can generate anything. I can show you the values. Let's see. So Gauss-Seidel things. Okay, so it's like 3 equations with 3 unknowns. Okay, it's only for 2 equations is given. Okay, so is there no flexibility to change the number of unknowns? We'll go to one more other calculator, Gauss-Seidel calculator with solution. Not working. Fantastic. Maybe this one, A to Z math. Then again Yeah, the equations is what we have. Good. Okay, so the equations. So let's see, calculator, if you can have, then enter your problem. Good. Okay, I'll enter my problem then. Gauss-Seidel. Okay, three variables you can type, I guess. Okay, so we'll type the three variables and we'll see. 2x minus y plus z. Let's zoom this so that you can understand the equations. 2x minus y plus z. Okay, so plus z is equal to how much? 2x minus y plus z is equal to 3. I'm just showing you because I just want to show the iteration values. This is 3. Good. Then 3x plus y equal to 11. X plus 3y minus z. X plus 3y minus z is equal to how much it is? 1 plus 6. 7. 7 minus 3. 4. This should be 4. Okay. This should be 4. X plus 3y minus z is equal to 4. Okay, x minus y plus 3z is equal to 8. Then what is the value? X minus y plus 3z is equal to 8. Good. X minus y plus x minus y plus 3z is equal to 1 minus 2 minus 1 plus 8. So this is 8. Okay. Now we are starting with initial guess 1, 1, 1, for example. Okay, 1, 1, 1. Okay, so this is what we are doing, the initial guess. Convert to diagonal dominant system, yes or no, you can decide. Okay, so if you want mandatorily in diagonal dominant system, you can convert, or else no. Okay, but anyway, we are keeping no because we have already set the equations in diagonally dominant systems. Okay, so number of decimals, let's say for example I want up to decimals and maybe 5 place accuracy. Let's calculate. Okay, so if you calculate 5 place accuracy and find, okay, so now it will generate the solution. So let's see. These are the equations. 2x minus y plus z is equal to 3. 2x minus y plus z equal to 3. X plus 3y minus z equal to 4. X plus 3y minus z equal to 4. X minus y plus 3z is equal to 8. X minus y plus 3z is equal to 8. Good. And these are the initial guesses. 1, 1, 1 is what I have taken, which I hope you can see actually. Now, if you look at the solutions, let's see what you get. First approximation. Okay, solutions after first approximation. This x1 value is 1.5, which we have got actually when you have done this calculation, 1.5. Second value means the second variable value after first iteration is 1.1667, 1.16667 since I have set 5 decimals, and z1 is 2.5556. Okay, this is after the first iteration values. This is what manually we have calculated for checking. Now, if you use these values of x1, y1 and z1, and if you perform second iteration, you would have got the values like, for next solutions, click on the link below adds. Where it is? Click here to display the next step solutions. Okay, please wait for 8 seconds. Okay, 5, 4, 3, 2, 1. It's generating step by step, I guess. Okay, a lot of ads of course nowadays. So you'll see. Fine. So you'll see x2, y2, z2 values will be this. Okay, if you use that x1, y1, z1, and if you calculate x2, y2, z2, these would be the values 0.8, 1.9, 3.03. You can observe one thing. Our actual roots are 1, 2, 3 for this system. As you are performing these iterations, since it's a diagonally dominant system, this value is approaching 1, this value is approaching 2, and this value is approaching 3. Can you find this? Yes or no? Correct? Because we know the actual roots, we are comparing. Okay, since you know the actual roots, in the second iteration, when you go to the second iteration, the values started going towards the actual solution. Yes or no? Because it's clearly a diagonal dominant system, it should go for convergence. So you can see this is going towards 1. Initially it's 1.5, now it came to 0.8. Okay, it is 1.67 whatever, it's coming towards 2, this is coming towards 3. If you go for the third iteration using these values, if you perform the third iteration, you can see this value has moved from 0.8 to 0.93, which is much close to 1. This value has moved from 2.2 or some 1.98 something to 2.03, again close to 2. This value is close to 3. Then again, fourth iteration values, you can see 1.00077, 2.01003, and this is 3.003. If you go for fifth iteration, you can understand this is 1.000, this is 1.00, this is 2.01, this is 1.99, and this is 2.99. Okay, sixth approximation. Okay, so let's see 6, 7 approximations. Maybe we'll wait for some more seconds, 5, 6 seconds more. Okay, and we'll see. So basically the idea is, as you go towards the iterations, the solution definitely converges, and there comes a situation where the values between the difference between x, y, and z keeps dying down actually. Understood? Like you can see, 7th approximation 0.9999, 1.999. This is exactly 3. So it has given the solution x is equal to almost 1, y equal to 2. I hope you can see this. X equal to 1, y equal to z equal to 3. If you look at the tables, okay, nice tabulation is given. These are the x values, y values, z values in the iteration. This is the iteration number and this is the x, y, z. So in the first iteration, we have x as 1.5, y as this, z as this, okay. But if you keep scrolling down the third, 5, 7 iterations, the difference between these things has come up way down, okay. 1.000, 0.999, 1.999, this is almost 3, okay. So you will eventually find out the difference between these values will actually come very small and the error would be much less, and finally you will yield the solution actually. Clear? So you write a for loop for I equal to 1, or you can check this using else condition also. Clear? So this method is there in ESC syllabus, W syllabus. In electrical syllabus, they can ask you, see, if I'm telling you, they can ask you what is the value of y after first iteration. Okay, these kind of questions they can ask you. Clear? Clear to all of you? Okay. So this is Gauss-Seidel, which is again this is very faster compared to Gauss-Jordan. The meaning is, in case of Gauss-Jordan, you won't update intermediate. You will perform all these iterations only with xi, yi, then you will go for the second iteration. But in the first iteration, here once you get the value of a variable, you will immediately update the variable. Okay, so that's why this method is faster convergence. This method will converge fast compared to Gauss-Jordan. Okay, that's why. In Gauss-Jordan, what we'll do is, we don't update this immediately. Okay, we'll update this at much means you will calculate xi plus 1, yi plus 1, zi plus 1, then you will update all in the next iteration step. But here you will do intermediate updation so that convergence is fast. Clear to all of you? Okay. Is this clear? Thanks for the love. Clear to all of you? Did you all understand this Gauss-Seidel? A very powerful technique actually. Okay, because when I'm doing 3 by 3 and all, you may feel why he's doing all these things. LU decomposition gave much faster, Gauss elimination came much faster. But when you go for very large number of systems, these are the actual methods which, you know, your Casio calculator, okay, what you use in your engineering, every calculator computer is designed based on these algorithms. Yeah, nonlinear dynamics, it's useful. Okay, at many places, see, whenever the complexity of the system raises, ultimately the classical methods like the Gauss elimination or basically this LU decomposition, these things fail. Okay, or fail in sense, or else they'll give very laborious calculations, but these will never fail if you have a diagonally dominant system. Okay, intentionally I have set this as diagonally dominant because it guarantees a solution. In examination, in gate examination, please read the question thoroughly and come to know whether they want you to convert to diagonally dominant and then apply this algorithm, or for the system as it is, they want you to apply this algorithm. Because sometimes, as I told you, it need not be mandated to convert to diagonally dominant. So that will be given in the question. So please check. Okay, thanks. Yeah, so many hearts are floating. Good. All of you understood this? I'm pretty much sure in your life, many of you might have understood matrices in a different way for the first time. Correct? Especially at the points like eigenvalues, eigenvectors, diagonalization, then these kind of system of equations, concept of a rank. Okay, when we are writing determinants, again some nice points about determinants, a into h joint a equal to a into I, how all these things has turned up. I think many of you might have understood with very much clarity actually. Correct? Okay, but anyway, time is a bit short. So in tomorrow's class, before starting calculus, I'll spend some 10 minutes on doing SVD, singular value decomposition is a bit important. And also if time permits, I'll talk about Skur's complement in partition matrices, because these things are important actually for data science exclusively. So we'll talk about these things and then we'll start basic calculus. Okay, single variable calculus. Clear? Yeah, in matrices, many of you feel like you don't get explanations. People tell you do this method, you should do this like this, and that's how people do. But there is an explanation behind each and everything. Clear? RK methods, ODE, numerical methods. Okay, we'll see. In numerical methods, we'll see Ivangi-Kutta fourth order method. Okay. Fine then. Okay, so anyway, we'll close for today because the time is up. I have, as I told you, there's a Telegram live which I'm going to start in next maybe 10 minutes. By 9:10 roughly we'll start. Okay, so in today's class, the main focus was on vector spaces initially. Then we focused a bit on what we did today. Basically, I've forgotten. We have done some things, no? Something useful. Yeah, vector spaces, span is what we have covered. Then linear combinations I have finished yesterday. So methods is what we have seen. Basically Gauss elimination, LU decomposition, and Gauss-Seidel is also what we have seen. Okay, so in tomorrow's class, as soon as I start the class, we'll definitely. So what an exactly adjoint of a matrix give us practically? To convert a given matrix into diagonal, of course. Okay, to convert a given matrix into diagonal, that, you know, because it's always easy to deal with diagonal systems. So adjoint is that particular matrix which when you multiply to any matrix will convert that matrix to diagonal matrix, of course. Okay, so that the calculations would be much easier. Fine. In which Telegram chat? There will be Telegram chat. Yeah, Telegram live. You can even on your cameras if you want. So this is the location. This is the group where I'm going to conduct Telegram live in next maybe 10 minutes kind of thing. Okay. So is that clear to all of you? So I hope all of you enjoyed matrices. Of course, there is much still, but I have restricted myself to talk only about things which are within the GATE syllabus. Okay. Otherwise, if I keep teaching matrices, I can extend till maybe next 2 months. But you know, there is always a limit for things. GATE syllabus and all. We are working within the GATE syllabus domain, so we are not going out. See, will there be Telegram chat? Yes, of course it is. Arc method, ODS will deals. Exactly adjoint, I told you it. If you multiply adjoint of any matrix to itself, then ultimately the combination gets converted to a diagonal form. Okay. Like for example, if you want to calculate AX is equal to B. Okay. So let's say, I'll just tell you with help of an example. So it will be better. If you see, if you want to calculate AX is equal to B. Okay. Then ultimately, it's like inverse may not exist, but adjoint can exist, right? So if adjoint exists, and if you multiply A into adjoint A into X is equal to B, then ultimately it converts this matrix into a diagonal matrix, correct? Some constant determinant of A into identity matrix into X is equal to adjoint A into B, of course. This is what you'll get. Okay, and this matrix is a diagonal matrix, so ultimately it's easy to solve. So fine then. So we'll meet again tomorrow at 7 PM. We'll start basic calculus. I mean the single variable calculus, of course. A bit of important understanding on functions. Again, limits, differentiation, continuity. We'll talk about all these things. Which unit will you teach us? That's what I'm telling you. Single variable calculus. Okay. So single variable calculus is what I'm going to start tomorrow. Calculus, a bit of important graphs, nice stuff. We'll see. Okay. On Desmos again. So we'll understand. Again, this will be in English. So please do attend. So tomorrow, even since you have seen the feedback and all, if your friends are also willing to attend, you can make them attend the class so that they'll also learn, because it's for free. It's 100% free, you know. And you know, definitely this kind of content coming for free is like a big help if you get 2025. Okay. So you can call your friends in some other colleges, or if some of them are feeling hectic with matrices, you can call them. It will be helpful. Okay. One thing I did not teach you is quadratic form right now. Okay. Why quadratic form I didn't teach you? I'll come across in calculus again. So quadratic forms are much helpful in calculating maxima and minima. Okay. In multi-variables, in 2 variables or 3 variables, which we will see, of course. Okay. Differentiation of matrix is what I'll teach you there. It would be helpful. Okay. So fine. Thank you all. So join live in next 5 minutes. Maybe we'll start in the Telegram channel of mine. Okay. 𝐂𝐤𝐬𝐿. Yeah, 𝐂𝐤𝐬𝐿 I forgot. Okay. In tomorrow's class I'll teach. Okay. It's a very simple thing, of course. Basically, 𝐂𝐤𝐬𝐿 theorem tells you every matrix satisfies its own characteristic equation. That's it. Okay. Anyway, we'll talk about that 𝐂𝐤𝐬𝐿 theorem in tomorrow's class. No issues. Okay. It's very simple, of course. Every matrix satisfies its own characteristic equation. Obviously, it should satisfy it. Okay. So 𝐂𝐤𝐬𝐿 we'll talk in tomorrow's class. No issues. Okay. Yeah. Thank you all. We'll meet tomorrow. We'll start single variable calculus in tomorrow. So you can come and you can bring in your friends also if needed. Bye. Take care. Join that live in Telegram channel. We'll start in next 5 minutes. Yeah. Okay. Bye.